Hi guys, welcome to the lesson of partial differential equations. So we were discussing canonical forms, and in the previous lesson we discussed about the general canonical forms and the phenomena of constructing the canonical forms, and then we discussed about hyperbolic equations. We discussed about their characteristic equation and the characteristic phenomena, right? So now we will talk about the parabolic PDEs. So in the previous lessons, we discussed that if the discriminant of the given equation is equals to zero, then when we call it as a parabolic partial differential equation, right? So the rest of the case is same. In fact, in this parabolic PDE, you just have to now. Yes, we can see that this is the characteristic equation for the parabolic PDE. And what's the difference between the parabolic and hyperbolic PDE's characteristic equation is that we will get only one root from this equation, because you can see that this is b over 2a, right? So we will only have one root from this equation, and we will name it as psi, right? Psi is equals to the root. But what about the second root, that is eta, right? So for eta, we will assume a root by ourselves such that the condition of Jacobian should hold, right? So we talked about this condition of Jacobian as well. So this Jacobian should not be equals to zero, such that we can assume any value for eta, right? And then we can find the Jacobian, and if it's not equals to zero, then it's fine, and you can carry on for the solution. So this is some general discussion about the canonical forms of parabolic PDEs. So now let's talk about some examples, because rest of the things are same: ux, uy, uxx, uyy, uxy. So let's talk about a question, right? Let's say the question is given: uxx plus 2x uxy plus x squared uyy plus uy minus 1 is equals to 0, right? So the first thing we need to do is we will apply the discriminant rule, right? So we'll check either this is equals to 0, greater than 0, or less than 0, right? So a the coefficient of uxx is 1, the coefficient of uxy is 2, the coefficient of uyy is x squared. So we'll put in the respective coefficients into this equation, and then we will see that this is equal to 0. So this is a parabolic equation. Then we have the characteristic equation, we talked about it earlier, that is dy over dx is equals to b over 2a, which will be equals to 2x over 2, right? Because b is 2x and a is 1. So this will cancel out, and we will only left with x. So dy by dx is equals to x, and this is a separable ODE, so we can integrate it. So let's do that. We integrate dy is equals to x dx, and after applying the integration, we get this c1 is equals to y minus x squared over 2, right? So this is one of the characteristic equation, but we talk about the second root, that we said that we can use, we can choose any function of x and y for the second root. That may be x, or that may be y, right? Or x squared, y squared. But what we need to do, we need to check the Jacobian, right? We need to check the Jacobian after choosing eta. So if the Jacobian is not equal to 0, then it's fine. We can carry on for our solution. But you should keep in mind that choose such eta that should be simpler, right? Don't choose a complex eta. Just you can choose x or y. It's enough, right? So it's the best to choose x or y, right? So Now I have chosen eta is equals to x, right? So I have chosen eta is equals to x, and now I'm performing the Jacobian, right? So I'm solving for Jacobian. So psi x will be what? From here, if we differentiate with respect to x, it will be negative 2x over 2, then we're left with negative x, right? So here is the negative x, that is psi x, then psi y will be equals to 1 when we differentiate this with respect to y, right? And then eta x will be 1 because eta is equals to x, and when we differentiate with respect to x, we will get 1, and then this is 0, right? So it's simpler. This multiplied by this 0 minus 1 into 1 minus 1, and that is not equal to 0, so we are done. Our choice is perfect, right? Because the Jacobian is not equals to 0. Then we will calculate these all psi's and etas because we are going to use it in the equation, right? So I am underlining them, right? So now we have to find uxx, uyy, because you can see in the question it's given uxx, uxy, uyy, uy. So we need 4 elements, right? So we need 4 elements. So let's do that. So uxx, this is the equation, right? One implies that uxx plus 2x uxy plus x squared uyy plus y minus 1 is equals to 0. So now we have to find uxx and uxy. Right. So we are finding uy first. So uy is equals to u psi times psi y plus u eta times eta y. Then we will multiply u psi times 1 because psi y, the value of psi y is 1, plus u eta times 0 because eta y will be 0 because eta is equals to x. So eta y will be 0, definitely 0. And then uxx, for uxx we know that this is the form u psi times psi x squared plus 2 u psi eta and this whole equation, right? So we know that now we are plugging values here and here, here and here, right? So here is the value for psi x, here is the value for psi x, this is eta x, this is eta x, this is psi xx, and this is eta xx, so it's 0. Here you can see the values, right? So, and then similarly for uyy, uyy is equals to this form, and it's more simpler because we are only left with the u of psi, all other components are 0. Then for uxy, we'll get this one non-zero term and then this with this one, right? So we are left with only 2 non-zero terms, that is negative x times u psi and then plus u psi eta, right? So we can write here this is equals to negative x times u psi plus u psi eta, right? So let's move on. Now we found uxx, uxy, uyy, and uy. So we'll plug in equation number 1. So here is the equation number 1, right? So now we are plugging the values. So for uxx, I plugged u psi x squared times u psi. Let's write the original equation first. So this is the original equation. So let me write it again here. U double x plus 2x uxy plus x squared u double y plus uy minus 1. Okay. So it's u double x first, right? So what's u double x? This is our u double x. Yes, this is our u double x. I can write it as x is squared u psi minus 2x u psi eta plus u eta eta and then minus u psi, right? So I can plug this instead of u double x. So similarly, I've written in this manner, right? So this is x squared u psi psi, this is negative. Just look here, we are putting this in uxx, right, in place of uxx. Then we are given plus 2x times uxy. So uxy we found like this. Where is uxy? This is uxy. Then plus x squared uyy. Here is our uyy. And then plus uy, that is u psi. We get uy as u psi. Here's u psi, right? And then negative 1. And now we are simplifying, right? So we can see that yes, here it's x squared u psi psi, right? Here it's negative 2x squared u psi psi, and here it is again x squared u psi psi. So this x squared u psi psi plus this x squared u psi psi will be 2x squared u psi psi, and then this is negative 2x squared u psi psi, so we can cancel these, right? Then we are left with the negative 2x, right? This we can use another color for this, but negative 2x u psi eta, and here it's positive 2x u psi eta, so we can cancel them, right? Then we are only left with these two elements, right? U eta eta and negative 1, right? Sorry, I forgot to tell about this one. Yes, this is negative u psi and this is positive u psi, right? So we will cancel them. So we are only left with these two terms. So this is the final answer, and this is the canonical form, the simplified canonical form, right? So this was our objective, and we are accomplished with this part, right? So we will move on to next question. The question says that 36y squared uxx minus 12y uxy plus u double y minus 6 times 1 plus 4y times ux plus 4uy is equals to 0, right? So first step is to check for the discriminant, right? So a is equals to 36y squared. This is the coefficient of uxx, and we can see that all these are the variable coefficients, right? So we are working on variable coefficients. Most of the time, the variable coefficients are like important because we just need to see the conditions for the variables where they are changing the classes of these differential equations, right? By taking different values. So this is 12y, it's b, and this is nothing because it's ux, it's coefficient of ux. We are not uh, dealing with coefficient of ux, so we need only coefficients of these, right? So hey, it's 1, right? So this is a is equals to 36y squared, b is equals to negative 12y, c is equals to 1, right? We put in the discriminant equation, and what we get 0. So it's a parabolic equation, right? So we know that for parabolic equation, the characteristic equation is given by dy by dx is equals to b over 2a. So we applied the form and we get negative 1 over 6y. This is separable. We separate the variables, we integrate it, we find the characteristic curve. So it's C1 is equals to 3y squared plus x, right? Now I named this C1 as psi, as we are doing, right? But what about the eta? Now, as I told you that we have to choose eta such that the Jacobian should not be equals to 0, right? So we can choose any value, or x or y, right? But just we have to check that the Jacobian should not be equals to 0. So in the previous example, I took x. Now in this example, I am taking y, right? And there is one more thing that you should keep in your mind, uh, that is the abstract, right, of these forms. These forms that says that this function should not be parallel to this curve, right? These are the curves basically, 3y squared plus x and the y. These are the curves, right? So it says that this y that we are choosing should not be parallel to this one, right? So, and this is the same thing like as we are doing Jacobian, finding Jacobian, because if this is parallel to this, the Jacobian will be equals to 0, right? So it's enough if we are calculating the Jacobian and it's not equals to 0, then we are done. We are fine with these values, right? So psi x equals to 1, psi y 6y, eta x 0, eta y 1, right? And we found the Jacobian, it's 1, it's fine, we are good, right? And then we found all other uh, derivatives, partial derivatives, right? These are worthy in whole of the lesson, right? We are dealing with them again and again continuously. So we will find ux, uy, uxx, uyy, uxy. Now you are very familiar with these, how to calculate these ux's, uys, uyys, and all these, right? So you are good enough with them now, right? So ux is equals to u psi, uy is equals to 6y u psi plus u eta, uxx is equals to u psi psi, uyy is equals to this term, and uxy is equals to this term, right? So now we will put all these values in the original equation. That's equation number 1, and equation number 1 implies this, and this, right? And again this whole equation. We just plug the values here, right? So we just plug the values. These are the values, right? These all are the values of ux, uxx, uy, uyy, uxy, right? Then we simplified, we expanded, then we will cancel out each things that are that we can cancel out. That is 36y squared. Here it's positive 36y squared. Here it's positive 36. It will be 72y squared u psi psi. Then here is negative 72. So I can cancel them, right? It's so easy. Then I have negative 12y u psi eta. Then I have positive 12y u psi eta. So negative and positive will cancel each other, right? And then we have positive 6u psi, negative 6u psi cancel out, right? Then we have negative 24y u psi and positive 24y u psi. That will cancel out. So what we will left with is u eta plus 4u eta, right? So now you can see that how simple form we get here. U eta plus 4u eta is equals to 0 from a lengthy equation. Now it's easier to solve, right? Because this is like a second order differential equation. I can write it like this way. It's not actually a second order differential equation, but it looks like I can solve it like a second order differential equation, right? So we can write this equation as dawa a squared u over dawa eta squared plus 4 dawa u over dawa eta is equals to 0. Right now this equation is more easier to to solve than the given equation that was complicated, right? This is the equation. So how complicated is this? You can see that. All right, so from here we get to the conclusion that u eta plus 4u eta is equals to 0. So how cool is that? You can see it. It's very nice, right? So hope you guys understand this lesson of parabolic PDEs and their canonical forms. Now in the next lesson, we will come up with the canonical forms of the elliptic equations. All right, so we are done with parabolic and hyperbolic equations. So we'll talk about elliptic equations. Elliptic equations are also easy, and by doing more and more practice, you can make it more easier to yourselves, and you can take some questions from books, from internet, from anywhere that you can find these questions. And these are very important topics, canonical forms, right? So you should be familiar with these solving for canonical forms, because in the second order partial differential equations, when we want to solve them with especially when they are with the variable coefficients, so we used to apply the characteristic method for the initial value problems. Then we drive these equations to their canonical forms, and then we solve it, because the given original equations are not always solvable, right? So it's easy to solve when we are in the canonical form. So we use these transformations, we transform the equations to their canonical forms, and then we apply the Cauchy's characteristic method, and it's easier to solve, right? So that's all for the time being, and thanks for watching.